Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about the semi-batch reactors. In the previous lecture we have discussed about the membrane reactors. Now what is semi-batch reactors? A type of reactor in which reactants are present and after a certain time we are adding or remove some component from our system. So semi-batch reactor are those reactors in which initially some components are present and we are adding or removing some component after a certain time to increase our conversion in the semi-batch reactor. So usually these are like a batch reactor, but in these reactors we are either adding or removing some component from the system after a certain time to increase our conversion in the system, which is called semi-batch reactor. So these are the various forms of semi-batch reactor. This is a system, this is semi-batch reactor. Component A is present in the system and after a certain time we are adding component B to our system. Similarly, this is also semi-batch reactor. Component B is present in the system and after a certain time we are adding component A to the system slowly and gradually. So similarly, we can also remove component B from the system after a certain time using some pump. So this is another semi-batch reactor. A and B are present in the system. Suppose component A is more volatile. If we are giving some heat to the system, then after a certain time component A will remove from the system. These are the CSTR in series. This is one CSTR, CSTR number 2, CSTR number 3. Component A is present in CSTR number 1. We are adding component B into the CSTR after a certain time. The product from CSTR 1 is going to CSTR number 2. And we are adding component B to the CSTR number 2. Similarly, this product is going to CSTR number 3 and we are adding component B to the CSTR number 3 from the side stream. So these three are the side stream. So this is also a CSTR, this is also a semi-batch reactor. Now this is another example semi-batch reactor. This component A present in the semi-batch reactor. And this is the volume of the system. This is the stirrer. Component B, after a certain time we are adding component B into our system. V naught is the volumetric flow rate of component B entering to the system. Suppose component A reacts with component B, it gives us the product C and D. So first of all we will write the mole balance to our system for this general reaction. This is a general reaction, irreversible reaction in which reactant A plus B gives C and D. First of all we will write the component balance on the components. So 4 components: component A, component B, component C and component D. The first step is write mole balance on component. So first of all we will write the mole balance on each component. Mole balance on component A, this is the general mole balance equation. Input minus output plus generation is equal to accumulation. A is not entering the system, so this is 0. A is not in the system, this is 0. The rate of generation of component A in the system is RA into dV over the whole volume. And the accumulation term is the component A is changing in the system. So the mole of component A in the system changes in this semi-batch reactor. So the RA into V is equal to D in A, where NA is the mole of component A, changes with the passage of time. So now this is the RA into V and dNA divided by dt. We know that mole is equal to concentration of A into volume of the reactor. So mole is equal to concentration, unit of concentration is mole per m cube into volume. So this cancel with this, so again this mole. So in place of Na we will write Ca into V. So we will write, in place of this Na we will write Ca into V. And take the derivative of this product function Ca into V. So first function is this one and second is this one. So first function into derivative of second, the second function into derivative of first function. So this is Ra, rate of component A, volume of the reactor, first function into derivative of second plus second into derivative of first. But we know that volume divided by time is nothing but volumetric flow rate. So this is the RA RA into V is equal to CA, and dV by dt is nothing but this one, volumetric flow rate volume dCA by dt. So divide this equation A by V, volume of the reactor. So we will get RA is equal to CA, volumetric flow rate divided by volume plus dCA by dt. Rearrange this equation, this term will come to this side, so it will be RA minus CA into volumetric flow rate divided by volume of the reactor, and this will equal to change in concentration in this immediate reactor with the passage of time. So this is equation number 1, which we obtained from the mole valence on component A. Similarly, apply mole valence on component B. Component A is present in the system, and we are slowly adding component B into the system. V0 is the volumetric flow rate of component B, CV0 is the concentration of component B, which are entering to the system. So input minus output, the generation is equal to accumulation. So there is no B is not coming out from the system, so this term will be 0. B is entering this, this is the generation and the change in the mole of component B in this system with the passage of time dt. Now this is the mole variance. So if B0 plus input plus generation is equal to accumulation. Now we know that mole of component B is equal to concentration of component B into the volumetric flow rate of component B, and this is the volume. This is the volume of component, volume of the reactor. So in place of NB we will write concentration into volume, concentration into volume. Apply the product rule. So first function into the radical of second plus second into the radical of first, and this is the RB into V, and this is B0. Now this is the input, the generation, and these are the accumulation terms. So in place of B0 we will write CB0 into volumetric flow rate, because B0 is equal to concentration of component B into the volumetric flow rate of component B. So this is the RB into V, and this is CB into dV by dt plus V into CB divided by dt. So now this term will come to the right side, and this term will come to the left side. So this is the CB0 into volumetric flow rate minus CB, and this dV by dt is nothing but volumetric flow rate V0, and this term will become negative minus RB into V plus V into CB by dt. So after rearranging we will get this equation, this V0 and this also V0, so it will, one V0 will come out, and this CB0 minus CB divided by V will be equal to minus RB. This will be equal to minus RB plus dCB by dt. So this will be equal to this term will be minus RB into dCB by dt. So this term is minus RB. Now mole valence on component C. Component C is not entering, not leaving. Rate of generation, accumulation, again in C is equal to concentration of component C into volume, because mole later into volume. So volume of the reactor. So simplify this relation, RC into V and D and C. In place of NC we will write CC into volume of the reactor. Again simplify first function, derivative of second into derivative of first, and RC into V. Now this is RC into V, CC into this one. Divide this equation by V, suppose equation number B, we will get RC is equal to CC into volumetric flow rate divided by volume, and change in the concentration of component C with the passage of time in the semi-batch reactor. Simplify this term, this term will come to this side and it will become negative. Similarly, for component D, mole valence on component D is D is not entering, D is not leaving, the rate of generation, and this is accumulation. So ND is nothing but the concentration of component D into the volume of the reactor. So when apply the product rule, So this is the first function into the derivative of second plus second function into derivative of first, and this dV by dt is nothing but volumetric flow rate. Now divide this equation by V, suppose equation number C. So we will get RD is equal to CD into volume divided by volumetric flow rate divided by volume of the reactor plus change in concentration of component B with the passage of time. So in order to obtain this term will become to the left side, and this will become negative. So this is the mole valence on component D. Now the second step is write the rate law. So suppose our reaction was A plus B give us C plus D. So the rate law for this reaction, like rate of change in concentration of the rate of component A, which are consuming in the immediate reactor is K into C A C B C C. So there are two in reactants, so C A into C B. So this is the rate law for elementary reaction. Rate law, write the rate law. In the third step, write the relative rates. So the relative rates of the reaction type, this is the irreversible reaction. So change rate of component A which are consuming in the system is RA divided by minus 1 is equal to RB divided by minus 1 is equal to RC divided by plus 1 is equal to RD plus 1. So the stoichiometric coefficient here is 1, 1, 1, and 1. For reactant we are writing negative. This is negative because these are reactant, and for product we are writing plus sign. So minus RA is equal to R, minus RB is equal to RC is equal to RD. So this is the relative rates for the irreversible reaction, for the above general irreversible reaction. So in the fourth step, write the concentration is a function of component, any component. So concentration of component A is equal to Ct naught, the initial concentration of component, and the molar flow rate of component A, the total molar flow rate of component in the reactor. And that for isothermal system, the T naught will be equal to T, and for isobaric process P is equal to P naught. So similarly for component B, Cb is equal to Ct naught into flow rate of component B into Ft. For Cc, Ct naught into Fc divided by Ft. For Cd is equal to Ct naught into Fd divided by Ft. Now this Ft is equal to the total molar flow rate of component in the system, in the semi-batch system. So Ft term will be equal to the flow rate of component A plus component B plus component C plus component B, because there are 4 components, A plus B plus is equal to C plus D, so 4 components. Similarly, the Ct, what is Ct naught? Ct naught is nothing but the concentration. So this is the P divided by R into T naught, the initial temperature, initial pressure, and the universal gas constant. And this is obtained from the universal gas law. P is equal to nRT. So N divided by V is nothing but concentration into RT. So C is equal to P by RT. So you can get Ct naught from this relation. In the fifth step, combine the rate with mole valence. So combine rate and mole valence. So this is obtained from the mole valence. We obtain this relation. This is the rate and this is the mole valence. So similarly, in place of RA, we can write this rate that minus RA is equal to Kc ACB for elementary reaction. So in place of RA, we will write minus to this side, so minus. In place of RA, we will write minus K into CACB minus CA into this one. Similarly, RCB for component B, this is the mole valence and rate law. And in place of RB, we can also write it. In place of this RB, we can write RA, because RB minus RB is equal to minus RA RD. Minus RB is equal to minus RA. So this will cancel with this. In place of RB, we can write RA. Similarly, this is mole valence for component C. In place of RC, we can write minus RA. So in place of RC, we can write minus RA. In place of RD, we can write minus RA. So this is a mole valence and rate combination. So these are the mole valence and combination. Mole valence and combination. So this was all about the semi-batch system. In the coming lecture, we will use we will use polymer to solve that flow rate. The molar flow rate is a function of volume of the reactor. So we will use the ordinary differential equation, the ODE solver, to solve the problem. So this was just introduction to a general irreversible reaction for semi-wave system. Thank you very much for your attention. If you are new to the channel, please like and subscribe. Thank you.